Hi, we present our CoRL submission on learning object manipulation skills via approximate state estimation from real videos. A key motivation of this work is that designing rewards can be hard. Classically, rewards are handcrafted for each task, and it can be quite challenging to select the right hyperparameters. We discuss two previous works that learn to perform tasks using video demonstrations. Time-contrastive network learns a visual representation on multiple views and trains a policy based on visual similarity. Compared to TCN, our approach does not require multiple views, nor extensive training data. The second work, Deep Mimic, estimates the human pose in videos of people performing full-body activities and trains a policy to mimic their trajectory. While Deep Mimic focuses only on the human skeleton, we are able to learn object manipulation skills by a coarse modeling of the hand and object. In this paper, we consider three questions. First, we are interested in finding ways to learn to perform actions by watching a single video. Based on the input video demonstration, our model estimates coarse 3D state trajectories for the hand and object that can be used to train a policy to perform the action by a robot. We also showcase how using multiple demonstrations allows us to learn a robust policy. Finally, we show that a policy learned via automatic domain randomization generalizes well to varying initial positions and sizes for the hand and object. We show some results of our trained policies on the simulator and the real robot. Here, we ask the robot to watch some videos of the action shown in the top right corner and learn to perform the action, pull left to right. Note that the motion, left to right, is performed with respect to the robot, and the direction is therefore reversed in the real robot video. We ask our robot to push an object from right to left. We ask our robot to pick up the cylinder. Finally, we show an action that involves spatial relationships between two objects. Here, the robot is asked to put the object in front of the one on the table. We present an overview of our approach. Different from previous works, we adopt a two-step approach. The first step uses advances in visual recognition and differentiable rendering to extract approximate 3D state trajectories for the hand and object. We propose an optimization process that finds trajectories that are perceptually similar to the input video. In the second step, we use reinforcement learning to train an agent to mimic these trajectories. We term the process of going from a real video to a 3D simulated space as real-to-sim. Through visual recognition models, we are able to obtain segmentation masks for the hand and object that we track using a Kalman filter. Our 3D space approximates the hand as a cylinder and the object as a cuboid. We use two types of losses. A perceptual loss encourages similarity between the renderer, output and segmentation tracks, while physics-based losses model hand-object interactions, regularize motion, and ensure a fixed object size for the video. We show results for state estimation on a single video from each action. Each column shows the original video, the tracked segmentation mask, and the rendered approximate 3D state space, obtained through a differentiable renderer. Here, we show results of state estimation for actions involving two objects. In the second step, we first automatically align multiple trajectories extracted from the video demonstrations. These trajectories are used to construct a reward function for training a policy in randomized environments. Randomization assures the robustness of the trained policy. We present results where our trained policy performs single object actions both in the simulator and on a real robot. Note that these policies are trained on 6 videos per action, even if only one is shown as a reference. Similar results can be seen for actions involving spatial reasoning of two objects. Putting something onto something is very challenging, and our real robot fails at this task. To perform quantitative evaluation, we propose a benchmark in the simulator. We generate 1,000 test samples by varying the object size and gripper position and orientation. Trained policies are evaluated on these examples to study generalization and robustness. We handcraft metrics for each action based on the object and hand trajectories as executed by the policy. Our metric is a binary measure of whether the action is performed successfully. Green regions in the pull or push actions show valid hand orientations, while in the put actions indicate valid positions for putting the second object. We demonstrate the benefits of learning a policy from multiple videos by comparing them against policies trained on individual videos for all actions. In addition, we compare the proposed multi-video reward function to deep mimic that computes the reward by maximizing over the trajectories. Overall, our proposed approach works well on a majority of the actions. Additional results are shown as web pages accompanying this supplementary video. The first web page shows segmentation masks and rendered outputs of our approximate 3D state space for all videos, using all three methods discussed in the paper. The second web page shows a success and failure case of our trained policies in the simulator, along with the result of transferring the policy to a real robot. Our robot is able to successfully perform 8 of the 9 actions. Thank you for watching this video, we hope you liked it. Please find the web pages in the other supplementary file.